here, A at n minus B at n, we said this is A minus B times the sum from k equal to 0 at n minus 1 of AK B at n minus 1 minus k. And we didn't finish the proof of this. This is the same as A minus B. I'm going to open up this sum here. The first term, who's the first term? K equals 0, A at 0, right? So the first term is B at n minus 1 plus AB at n minus 2 plus A squared B at n minus 3 plus A at n minus 3 B squared plus A at n minus 2B plus A at n minus 1. I think you should have seen this formula before. This is for any fixed A and B. A and B are fixed, they don't change. N is the variable here. That is my P of n. That's what we left last time. Why is this true? It's actually quite easy to see why it's true. We're going to make a proof by induction, of course. That's the purpose. But you can see why it's true just by opening up this parenthesis here. Right? There will be a lot of terms that go out. So if I, for example, multiply A with this guy, what do I get? A squared B at. Now, is there a term here that when I multiply B with that, I get the same? Can I multiply this B with something to get kind of the same?
A squared B
These multiply with this, right? Will give me what?
Negative A squared B n minus 2.
Is that the same? So they will go away, right? You can see how a lot of these terms, when you open the parentheses, will just go away. Because that goes away with that, so on and so forth. What are the terms that do not go away? A times n minus 1 will be what? A at n. And the other one that doesn't go away is B times B at minus 1 minus B at n. So that's going to give me the formula. That's actually the simplest proof of this. Open up this parenthesis, show that all the terms go away except B at n with A and n, and that I have those two left here. Who's following me here? Okay? Let's recap the thing. My exercise here is a proof by induction, so that's what I'm going to do. But there's actually a simpler proof than that. Just open up this parenthesis, show that's a telescoping series except for two terms. So we do this. The other thing that were left there that we have to do, we have this recurrence, was it n plus 40 of n by 2? That's kind of like merge sort, except it's not 2 halves, it's 4 halves in here. And we already did the intuition. What was our intuition? You guys remember? Or can you look at the notes? We said that T of n is supposed to be kind of like what? N squared. So what this theta means, this is order of growth. It doesn't say it's n squared. It's like n squared. So we said, what does this mean? There are two constants such that the T of n is smaller than Cn squared and is bigger than Dn squared for all n starting at some point. Right? So we already did the intuition last time for this. We kind of figured out, hey, this is about n squared because how the intuition go, we open up these few steps until we kind of figure out what do we think is. But then we still need to make this proof by induction. Okay, so those are the first two things that we're going to do. I put them here just to recap what happened last time. The first one's in here. What is my P of n plus 1 here? That's what I want to prove, right? that this by induction, there'll be a base case and an induction step. So let's write down P of n plus 1. How do I read this formula for n plus 1, not for n? A minus b stays the same. And what's the sum becomes? K equals 0 to n of a at k, b at n minus k. Very good. That's what I want to prove. So let's see here the base case. I think we did those last time, but just a quick recap. How about n equal 2 base case? What is this formula going to be? A squared minus b squared is a minus b times a plus b. Do you guys remember this formula from high school?
Yes.
That's like how people do, you know, when they ask you what is 97 times 103. Some people do that very fast. How do they do it? What's 97 times 103? Can you do that mentally? Of course you can. 97 is what? 100 minus 3? Who's 103? 100 plus 3. So according to the formula, this is supposed to be what? 100 squared minus 3 squared. That's easy to do. How much is 100 squared? 10,000 minus 9? 9,991. That's the answer. Okay. How about n equal 3? The formula would be a squared, aq minus b cubed is a minus b times b squared plus ab plus a squared. Okay, so we have base cases. How about the induction step? It's here. We want to show, this is simple induction, it's not the kind of complete induction or strong induction. It only uses P of n to prove P of n plus 1. So P of n plus 1 is right here. That's what I want. And again, in the induction step, to prove P of n plus 1, I'm using P of n. That's what induction step does, right? It says, I want to prove this, and I'm going to use in that proof the fact that this is true for n. So the way I'm going to prove this is by starting on the right side here. I'm going to say, who's a minus b times that sum? Who's that? So what I'm going to do here, a minus b stays the way it is. I'm going to take, there's a term in here that contains only a's. See, there's a term in here that contains only a's, no b's. I'm going to take that term separately. So what's that term here that contains, what's the corresponding k so there are no b's? N. I'm going to take that one outside, separate. I'm going to take that term is the term for k equal n, right? That I write down separately. Then I have a sum which is from k equals 0 to n minus 1. So what happened here, this is a sum from k equals 0 to n. I still have a sum of the same thing, k equals 0 to n minus 1, plus the term for k equal n. But the term for k equal n I took out of the sum, I put separately. Who's with me? Okay, we need more hands up so we can continue here. Facebook can wait a little bit. I had a sum of k equals 0 to n. I have the same sum here from k equals 0 to n minus 1. That's exactly the same thing. But there's one term which is not in the sum, the term for k equal n. That term I took outside and I calculated. I say k equal n is a at n times b at 0, so I put it here. Now, the next step, a minus b stays, of course. This is a at n plus. I notice that everyone in here has at least one b. Of course, because I took the term with no b's outside. So everyone remaining inside has at least one b. right? The minimum is for k. What's the one that has only one b? N minus 1. So what I'm going to do, I'm going to take a b common factor because everyone has a b in there. I'm going to take a b common factor. So that's k equals 0 to n minus 1. But remember, 1b is in front of the sum now. So who's going to be inside? A at k? N minus 1 minus k, right? Because again, everyone has at least one b. So I took that b common factor in the front, and then the exponent, instead of being n minus k, it's a minus k minus 1. It's like if somebody had 17 b's in here, it will be 16 b's now, and the b in the front. If somebody had 3 b's, there will be 2 b's and 1 in the front. Other than that, it's the same thing. So now, we're going to open this parenthesis. We're going to say that's a times a to the n is a to the n plus 1 minus b times an. Right? I'm opening up those an times those two. For the other term, this sum, I'm going to leave it as it is, a minus b times b times this sum of k equals 0 to n minus 1, ak, b at n minus 1 minus k. Do you follow this? A minus b times an is in here. And then n minus b times this sum is in here. Now it's time to apply the induction hypothesis. A at n plus 1 minus b a to the n plus. The induction hypothesis tells me how much is a minus b times this sum. Right? Look at it. It's right here. Again, n minus b times this sum here. This is the induction hypothesis except for this b. This b is not in the statement. But a minus b times this sum is exactly the right side here. So we can say this thing together without b is Pn right side. So how much is that? B has to be here because I don't have a b, so I take this b. How much is a minus b times this sum from the induction hypothesis?
A to the n minus b.
It's a to the n minus b to the n. Again, here's the right side. It's a to the n minus b to the n. Who follow me? Good. So what is this? Now it's easy, right? This is a to the n plus 1 minus b a n plus b a n minus b to the n plus 1, right? This is b times a n is b a n, b times b to the n is b n plus 1. This goes away with this. A at n plus 1 minus b at n plus 1, which is, of course, what I wanted to prove. That concludes my induction step. So the induction step, like before, proves that if I know P of n, and I use P of n here, I needed P of n, I can prove P of a plus 1. How do I prove P of n plus 1? I start on the right side, I do a bunch of derivations, including P of n, I use that, and I got to the left side. So that's the induction step. It proves P of n implies P of n plus 1. I have a few base cases, so that means this gotta be true for any n. Okay? Let's finish up that one too. This one in here. One of it, it's easy. The other one, it's, I wouldn't say hard, but just not easy. This part, I think it's easy. So how the induction step. So let's just call this is part A, and this is part B. So the part A induction step would look like what? What do I have to prove here? Is it a simple induction or is it kind of a strong induction? What step implies what? Is going to be a P of n implies P of n plus 1? Or what else is going to be there? It's strong, right? How did we do it before? We said if t of n by 2 is bigger than d, what would be this reading for n by 2? N over 2 squared. Then what's the statement for n? This is the induction step I need here. We discussed this last time. Why did I pick n over 2 and not some other ones? It's because n over 2 is part of the formula here. Right? And my induction step will be, if I find a constant, I'm going to pick up a constant eventually, but I need this to work. To say if it's true for the half, it's true for the whole. Right? Okay, so let's see how that would go. I'm going to say t of n is that n plus 4t n by 2. Right? So then what would I know from the induction hypothesis? This is bigger than n plus, I'm going to use the fact that t of n by 2 is bigger than this. Right? You guys remember how I did this before? I had to pick. So the one tricky part in here is to figure out how induction's got to work. This is obviously what I want to prove, is right here. But then this is P of n. What do I use to prove it? I use P of n minus 1, P of n minus 2, P of what? And in here, given all recurrences, we'll use internally the P of n by 2, whatever the terms are in here. So what happens if I say now, let's use this induction hypothesis. T of n by 2 is bigger than d n by 2 squared. 4 is a 4. And instead of t of n by 2, I'm going to put d of n by 2 squared. Right? That's coming from here. How much is this? N plus 4d n squared by 4, right? Because n by 2 squared, it's n squared by 4. So this is n plus d n squared. Correct? Because 4 goes away with 4. And what we want is to say this is bigger than dn squared. But that's what we want. Is that true? This is bigger than dn squared? Right. True if n is positive and d is bigger than 0. So I can pick any constant I want. For example, choose d equals 1. Again, d is a constant. I can choose whatever constant I want, but once I choose it, I cannot change it. So if I say d is 0.5, it has to be 0.5 everywhere. I can say it's 1, then it has to be 1 everywhere. So I'm looking at this equation here, n plus dn squared has to be bigger than dn squared. In your papers, not just in this course, from now on, whenever you write something like this that you did not prove, this is not something I proved, but it's something I wanted to be true. You clearly have to specify this is not something you proved, it's something you want. Right? So in here I say, that's what I got, this is something I already got, and then I want to say this is bigger than that. So I clearly state this is not something I know, it's something I want to happen. And then I say, well, that's true because dn squared is dn squared. All I need is this to be positive, right? And I choose a constant that I like. So that's good. I think that concludes it. This kind of recurrences, the base cases is t of 1 or t of 2. And we don't have to worry much about base cases because base cases are not specified. This recurrence, it only says the function has to satisfy this property. It doesn't say where it starts. It can start at t of 1 equal 20 or t of 1 equal 10. the same function. So we only care about the orders of growth here, how big it becomes. What this equation tells us, the left side, which you just did, is that this is going to be at least a quadratic function. It could be bigger, right? This we just proved here, it's bigger than something times n squared. It means it's some quadratic function or bigger. What is this equation going to say? So this one's saying it's at least a quadratic function. This is saying is at most a quadratic function. So the end result will be, this got to be like a quadratic function. Right? It's not much bigger or smaller than a quadratic function. Do we get that?
Yeah.
All right. So how would the induction step work for the other side? So part B. What would be the induction step? It's similar, right? I want to say what? What I want to prove is T of n is smaller than Cn squared, but what's the induction hypothesis here? T of n by 2, it's smaller than C of n by 2 squared. That's what I want. Remember all the examples we did before? We could do this kind of thing, and the equation worked out pretty good both ways. So we said, well, the only thing we had to do before was picking different constants. We say, you know, C has to be bigger, D has to be smaller, it worked out. This is one that doesn't work out that way. Let me show you why. If I try to do this, let's kind of repeat this reasoning here. I'm going to say, well, T of n is n plus 4t n by 2. I would apply the induction hypothesis here, this one. So it's n plus 4 c n by 2 squared. Is that right? Four is the 4. T of n by 2 is smaller than c on squared. Right? How much is this? N plus Cn squared, right? Right? What we want to show is this is, now we're going to say again, want. Very careful with this want. Want is not something I know. It's something I want to happen. I want to be this smaller than who? Is that possible? Can I find a constant C that does this for me? N plus Cn squared smaller than Cn squared? That has to be true for all n's. I can't say it's just true for n equals 0. It has to be true for all n's. Obviously, this is impossible. It doesn't mean the statement is wrong. It means the proof doesn't work. Maybe there is a different kind of proof that works. Okay? This only says that this kind of reasoning from half to the whole on the right side, that's the upper bound. It doesn't work this way. You can clearly see that if you want this to be smaller than that, never going to happen. You can choose any constant you want, a million, a gazillion. This will not happen. So this line of reasoning, no good. I still believe this is n squared. So there is a constant C that does the trick here. But I can't judge that way. I can't reason that way. So we need a trick. Let me just put this part here, bigger than dn squared. True for d for 1 and 1. So try 2. What we're going to do here is going to use a different induction that's a little stronger just to make this reasoning possible. We're going to say T of n is smaller than, so what we want is C times n squared. But what we're going to prove is a little stronger. C1 n squared minus C2 n. So I'm having two constants here. I can't prove it with just one constant. So I'm going to prove something a little stronger here. Obviously, if I prove this, I think that's true, right? If I can prove this is smaller than C1n squared times C2n, that's smaller than C1n squared by itself, right? So the C1 and C2 will be positive. Let me repeat this reasoning. If I manage to prove this, would that result immediately that this is smaller than a constant times n squared? Because it's a constant times n squared minus something. Right? So it's going to be smaller than this. But why do I choose to prove this? Because this works. The math on it works. It's actually a stronger statement. This is a stronger inequality than this that I want, because it proves something more than the n squared. Smaller, not just the n squared, but this minus something. So what the induction step would be here? It's the same kind of thing, but I will write it for the half first. If t of n by 2 is smaller than what, then t of n is smaller than c1n squared minus c2n. So that's what I'm going to prove. This is my proof here. What should I put here? This is for the whole, for n. How does this read for n by 2? How do I write this? Not for n, but for n by 2. Okay? That's what I want to prove. So this didn't work, but this will. And if we prove this, then we've got our proof, because what we proved is actually stronger than what we needed. So let's see how that goes. So proof. T of n is n plus 4t n by 2. So I'm going to use the induction hypothesis, this part, to say this is smaller than, n stays where it is. 4 is in the front of the t, and now t of n by 2 is smaller than this, so I'm going to write that here, c1 n by 2 squared minus c2 n by 2. If I open up this parenthesis, n stays. How much is this? With the 4, right? Oh, 4 went away? C1 squared, right? So the 4 goes away with 2 squared. Minus, how about here?
C2 and a half.
Times 4.
2, sorry, 2C2.
2C2 n. Right? Good. So we got there, and let's group the n's together. So C1 is with n squares, and n is what? I have one n here, minus 2C2, right? Now is the one part. What we want is what? We want this to be smaller than this, right? It's not this anymore, is what I'm trying to prove here. It has to be consistent. So this is C1 squared, n squared, minus C2n. That's what we want. Again, careful with those wants. This is not something I proved. It's something I want to happen. So how would this happen? For this to happen, what do I need? I think this is equivalent to say, well, Cn squared goes away with Cn squared, right? That's the same thing. So what am I left with? N times 1 minus 2C2 has to be smaller than minus C2n, right? So this is, n goes away with n, right? Because n is some positive number. So that means 1 minus 2C2 has to be smaller than minus C2. which is the same as saying if I move things around 1 smaller than C2. So I can choose, now I can figure out C1 can be 1, for example, because I have no constraints on it. But C2 can be, has to be, you know, something bigger than 1, for example, 2. So how did this work? I say, first of all, try the basic induction step, doesn't work. I'm going to try a stronger one. For people who know math and polynomials, what I did here was to say, my induction of a polynomial of degree 2 or quadratic doesn't work directly. So what I'm going to do, I'm going to still keep a degree 2 polynomial. It's n squared, it's still a quadratic function. But I'm adding a lower term. That's a trick used a lot with polynomials. If I can't prove something based on n squared or n cubed, the degree term. If a polynomial has degree 3, the main term is n to the cube, right? I'm adding lower terms. In here, I have a quadratic function. I've been added a linear term, which is the degree -1, and then the proof worked. Like before, I had to do some derivations to figure out what constants I need, but I can choose any constants. So choosing these constants, this stuff works. That concludes that recurrence. So overall, we prove this here, which means this T of n is like a quadratic function. I showed you this plot before several times. What this means is as n grows, there is a Cn squared, and there is a Dn squared. Those are the two functions. And T of n's got to be in between here. It's between Cn squared and Dn squared. That's what we proved here. We don't know exactly what T of n is, but we know it's kind of like a quadratic function.
What did you choose that the order of growth will be equal to n squared?
Yes.
But why?
In here, we did this last time. Remember? We open up this parenthesis for T of n and then T of n by 4 and so on and so forth. And we added up those terms. Anybody remembers that from last time? We thought that's kind of like n squared.
Okay.
And I want to add something which I said already. If you do that derivation very rigorously, you may end up with an n squared, provable n squared, so you don't need any induction steps. But that's tricky. It has a lot of sums with logarithms in it. If you do that very, very rigorously, that's called the iteration method or the tree method. It's in the algorithms book. Again, do it rigorously, will get you n squared. And you can stop right there. You say, I figured out already not intuition, but I figured out the proof, that's n squared. A simpler way to do it is just to get an intuition and then do induction proof, because these kind of things are much easier than that recursive iteration tree. So for most recursion that you're going to get, either in this class or in the algorithms class, you should do a few steps of the recursion just to figure out what you think that recursion is. Okay? You're going to learn in the algorithms class, not in this class. There's something called the Master Theorem. The Master Theorem, which I'm not going to state, I'm just going to tell you what's about. It has to do with all these recurrences that look like this. For any A, B, and C. So almost all recurrences that we did so far were of that type, right? This one right here, what's A, what's B, what's C? What is the A in that recursion right there? 4. What is B? 2. What is C? 1. How about the one for, we did I think one that was 2n by 2 plus n squared? What's A? 2. What's B? 2. What's C? 2. Merge sort was T of n is 2n by 2 plus n. What's A? 2. What's B? 2. What's C? 1. There is a Master Theorem who says, depending on A, B, C, there are 3 cases. depending on A, B, and C. If this is a dominant term, in some case, it will be, you know, n to the c. If this c is very big, like it was in here, n squared was the dominant term, so this ends up as n to the c. If this is a dominant part, then it ends up as being whatever comes out of this term. You can ignore this one completely. And if these are in the middle, there's a logarithm equation there that tells you there's a balance between them. Then it's a balanced case. You can easily find this theorem online in the algorithms book, so on and so forth. And I don't want to say it now because I specifically don't want you guys to go study it for the exam or nothing like this. I'm just saying a lot of recurrences of this form can be solved with just the formula directly. Like no derivations, no nothing. That's not all the recurrences. It's just the ones that have this particular form. So you're going to do that in the algorithms course. The only one recurrence that I have here left is T of n is T of n by 2 plus T of n by 4 plus T of n by 8 plus n. That's the last one I want to do. It's not of this kind, right? I cannot write it like A and 3 plus 6. So it's a different kind. Okay, so that's how do we do this one. We should first create some intuition to see what we believe this one is going to be. So if I start opening the terms here, what's T of n by 2? When I apply the same formula for T of n by 2. It's going to be 4 plus over 16 plus n over 2. Well, that's just T of n by 2. But then I have one for T of n by 4 that I have to open, right? What's that going to be? Let me put this in the front. N by 2 plus. This is n by 4 plus, right? Now what's the last term here? And now I have an n by 8 that I have to open. It's going to be n by 8 plus. When I apply the recursion for n by 8, what are the 3 terms? So I wrote it down this way so I can add up easily. That's n by 4 plus n by 8 plus n by 2, n by 4, n by 8. That is 7, 8 by 8 plus T of n by 4 plus 2 T of n by 8 plus 3 T of n by 16 plus 2 T of n by 32 plus T of n by 64. So now I have a lot of terms in here. What happens if I open it up again? Right? Well, how would you solve this problem? You need a little bit of intuition to get it, right? Because the first thing on a recurrence, the trick is to get a sense of where it's going. Once I get a sense of where it's going, then I can start with proofs and all that. But if I have no idea where it's going, how am I going to even start the proof, say by induction? So, let's keep the 7, 8 here, and let's see what we get. N by 4, it's going to be who I already have n by 4, right? T of n by 8 plus T of n by 16, right? Plus T of n by 32. That's T of n by 4. Actually, there's an n by 4 in front of it, right? Next one, T of n by 8. That's 2 n by 8 here, plus, when I open this, I get 2tn by 16, plus 2n by 32, plus 2n by 64. Is that right? N by 8. 2 is the 2 in front of everybody. So n by 8 is n by 16, n by 32, n by 64. What's the next one? 3n by 16. So that's going to be a 3, 32, plus 3, 4, plus 3, 128. That's the n by 16 term. Plus, I'm moving up to 2. Let's write another one here. 2n by 32. I'm going to have 2tn by 64 plus 2tn by 128 plus 2tn by 256. And the last one, which is n by 64, it's going to be n by 64 plus 128, 56, plus the last one is 512. So now I'm adding them up. What happened here? 7, 8 by 4 by 8 came from the previous term, right? So I'm getting here n by 4. This is another n by 4. How do I figure out how many n's are here? So 7n by 8 is from before, plus, let's say the denominator I want is 64. How many n's are here? If I think of a denominator as being 64. 16 plus, this is 64, this is how many n's here? 16. This is 64, so how many n's here? 12, because it's 4 times 3. How about here? 2 times 32, how many n's? 4 plus 1. Plus t of n by 8 plus how many t by 16? Plus how many by 32? How about 64s? How many 64s I got? 7? This is 6 again. This is 3. Okay. So, can I get an intuition of how big this is? What's up in here? 16 plus 16? 32 plus 16, that's 48, that's 49, is that right? Mm-hmm. So that's 49 plus, I guess, 56. That's the hardest part of this, yes?
What happens to the original n?
Oh yeah, you're right. I have another n from the original. This n here.
Did you do that to me? What did you do
What? This n by 2 I think comes from t and n by 2, right? So he's right. We need another n. So in here we'll have 64 plus, because there is a... Again, why am I doing this? I want to get an intuition. I told you guys, if you do this rigorously, you could perhaps end up with an answer and say, that's the answer. But this is hard to do rigorously. Look at this mess, right? Look at this mess. All we need is an idea where this is going. If I could guess from here, hey, I think it's like n log n. That would be enough. I'll go and make a proof. Now, my guess could be slightly off. Then I start doing the proofs. I figure out, that doesn't work, right? All I need is such an intuition. What I'm saying is that from this sum here, perhaps I do it another time, I could perhaps conclude that this is a linear function. Because every time I'm adding something, this goes so fast down with the exponential, right? These powers will go so much down. I don't think this exponent will compensate for that, these coefficients, right? The coefficients to me seem small enough to not compensate for n to the 256. That seems to be small. So in here, I'm looking at this and say, every time I'm moving on, I'm adding less than n, less than 1. Maybe this grows eventually some linear, constant times n. Right? So I'm saying there's some numbers, 1, 56 by 64, 49 by 64. Maybe I'll do it one more time. I don't want to do it in class. To figure out this might be something that is convergent. So eventually it's just a linear function.
So you're supposed to like start doing that until you get the intuition like right there when it's linear, and then do you do one of the proofs like that? There?
Yeah.
Okay.
So my intuition here is this. This will be insignificant, this whole thing with the exponents. The reason is it goes down too fast, the n by something, this something is going exponentially, while those coefficients don't seem to grow that much. I could be wrong, it's just a guess. So I say this whole part in here, maybe it's not significant. And in here, if I'm lucky, I'll keep adding things, right? The next time when I do this, there'll be another term. 49, who knows, might be 37 or something. But maybe the sum of them is actually convergent to something. So that's a constant times n. There's an n here, right? I did this example specifically for this purpose. So you can see how a messy thing may not need to be solved completely if it gives you some intuition. My intuition here again is this doesn't seem to grow that much. And this, maybe if I'm lucky, is just a linear term. So, intuition. P of n is P of n. That's linear. So, that's saying n plus t of n by 2 plus t of n by 4 plus t of n by 8. This is significant or dominant because that's a linear term, and that's insignificant. Right? It says that this part going down is not adding enough terms to make it count. You can think a little bit like in binary search. In binary search, that's kind of what happens in binary search, right? There is this is not part of binary search, but this is kind of the input array. To get the input array, I need to read all the values, right? So that's n. I read n values. How does binary search works now? It's assuming it's sorted, right? It starts somewhere. And then how the recursion goes. Once I compare the middle value, I decide what? Go there or go there? What would that be when I say go there? It means I have to now do the problem for a half. Right? And then, how do I do the problem for a half? So the binary search recursion, it's simply P of n is a constant plus t of n by 2. That's the binary search recursion. It just checks a comparison in the middle and then solves the half problem. And we know this is log n. Binary search works in log n steps. This is not exactly that, but it's close. It's saying, should t of n by 4 and t of n by 8 add up a lot more? If this ends up being like log n, it won't matter because this is already n. Right? We did this before when you say if you have two functions, one is n, the other one's log n, the bigger function is going to dominate this sum. So my intuition here is that this is about like binary search, although it's not just, it searches in a half and in a quarter and in an eighth. But still maybe that's only log n, and if that's log n, then the only significant part is this n in the front. One part, so what does this mean? What do I have to prove? T of n is smaller than Cn and bigger than Dn, right? Constant C and D. That's what it means to say it's linear. It means to say it's between constants of C on one side and D on the other side, just like before, except linear means n, not n squared. Did you guys follow me so far? It is true that there's a tricky part to recurrences, figure out where they go. That's not easy sometimes. Sometimes that takes a lot of messy arithmetics to get a good guess. Our guess here was n. Then it's simpler. That's what I want to prove. I would say I already know this. This is done. Why is t of n at least something times n? So look at it. It's at least 1 times n plus something, right? Right? So done for d equal 1 because t of n is definitely bigger than n because it's n plus something. So that's done. Let's do this. So the part B here is, what's the induction step here? What kind of induction? So obviously I want to end up with P of n, which is P of n is smaller than Cn. That's what I want to end up. But what would I need to prove that? My induction step here, it's going to be what implies this. I'm going to use strong induction, but I need more than just the half. Before we said if it's true for the half, it's true for the whole. Now we're going to need 3 properties, not just 1. So the strong induction argues you can use anything from before, right? You need to prove P of n, you can use Pn minus 1, Pn by 2, Pn by 3, P of 1, anything from before. Which are the 3 ones that we're going to use? P of n over 2, which says what? T of n over 2 is bigger than C, is smaller than Cn by 2, right? What else we going to use? N over 4, which says T of n over 4 is smaller than Cn by 4. And we're going to use n over 8. T of n over 8 is smaller than C times n over 8.
Is that just because those terms in the original T of n function?
Right.
Oh.
Like with any recurrence, what are the induction steps I need to prove the induction hypothesis? What am I going to put there to prove the whole thing? I'm going to say, assuming it's true for this, this, and that. So the strong induction allows me to use not just P of n minus 1, but any previous n. In this case, I'm using the half, the quarter, and the 1/8. Right? In the complete induction or strong induction, we can use any step from before n to prove P of n. Right? So I did sometime an example with a coin change that was using P of n minus 4. A lot of these induction steps were requiring the half or the fourth to do it. This one requires 3 of them, so it's definitely a strong induction because I need 3 properties to assume true to prove that one. But the proof itself is very easy. So T of n is n plus t of n by 2 plus t of n by 4 plus t of n by 8, right? So let's, that's the proof. What happens if I do the induction hypothesis here? I get n plus this I know these are smaller than Cn by 2 plus Cn by 4 plus Cn by 8, right? Which is, how much is the whole thing? N times 1 plus, how many, 1 by 2 plus 1 by 4 plus 1 by 8 is what? 7C by 8, right? Which is n times 8 plus 7C divided by 8. So I add up 1/2 with 1/4 with 1/8, and I got 7/8. And then, now what do we want? We want this to be smaller than what? Cn. So this is not something I know, this is something I want. Well, what would it take for that to be true? N goes away with n, right? I need what? 8 plus 7C by 8 to be smaller than C, which is the same as 8 plus 7C smaller than 8C, which is the same as if I move the 7C there and I make the subtraction, I get what? C bigger than? So I can choose C equal 10, bigger than 8, and that's going to work out. I want to make sure everybody understands how this want works in general. When I say mathematics proof, da 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 da, want doesn't mean I know it. It's I want it. So I'm going to explain what I need to make that happen next. So I've got this all worked out up to here. And then I say, what we want is this to be smaller than that. It doesn't mean we know it. It's that we're going to figure out the C now to make this inequality work. Then we find out all we need is any C bigger than 8. So we can choose 10, we can choose 100 or 1,000, and it doesn't matter. Anything bigger than 8 will make this work. So what we proved here is this induction step. That if you know this and this and this, you get that. That's strong induction, of course. Because it doesn't use only n minus 1 implies n, implies it uses any subset of the previous properties to prove the P of n. So we got this to work. P of n is at most a linear function, but because it's n plus something, it's at least a linear function. So what it means is T of n is a linear function. It's between two constants of linear. So if you look at the graph, this is Cn is a linear function, right? Cn. Dn is a linear function. They're lines because they're linear functions. So this is T of n is somewhere in here, between two lines. Okay? So you can expect a question in the exam or the homework about recurrences, right? It won't be that one. But keep in mind there's two parts. One, I have to get an intuition of where this is. Now, it could be trial and error. Maybe I make a guess, and my guess it's a little off. I try again. That's okay. I need to get a sense. Somebody gives me a recurrence. Okay, is this like linear? Is it quadratic? Is it like n log n? What is it? And then once I find a guess, once I get something, well, how do we prove it? And you'll see recurrences more in the algorithms class. Now, that's about recurrences. We have one more, which is a very famous one, but that one is not a growing function. It's one of the base. So you might have heard of Fibonacci numbers. They say F0, the first one is 0, the second one is 1. It starts with those three, And then what's the rule for the next Fibonacci numbers? Anybody knows? How do I get the next Fibonacci number?
F is F2 plus F1.
What?
So the current element is the element before plus the element before that.
The sum of the previous two.
Yeah.
So this one will be
3, 2, 2, 3, 5, 6.
okay, F was 3. So let's put a bunch of them here. F6, F7, F8. So F6 would be 8, right? F7 will be 13, 21, F9, 34, F10, F11, F12,
144.
So the Fibonacci numbers are defined F0 equals 0, F1 equal 1, and then Fn plus 1 is Fn plus Fn minus 1 for every n, which is at least 1. So it gives the base. It tells you, this is kind of a recursion. I could have written it in this way here, right? Fibonacci recursion is T of n plus 1 is T of n plus T of n minus 1. That's the same. Whether I write it with F's or with T's is the same exact thing, sum of the previous two. But in here we have a clear base. Usually recurrences, we don't specify where they start because we don't care. We only care of how they grow. In Fibonacci, the base is given. So it's not changing. Okay, so there are a bunch of things we want to prove about Fibonacci numbers, not just one. The first one that we want to do is to say, here's a magic number, perhaps you heard about it, golden ratio. Golden ratio number phi is 1 plus square root of 5 divided by 2. We'll take a look in a moment at it. And the complement is minus 1 over phi. Let's put it like that, minus 1 over phi, which happens to be 1 minus square root of 5 by 2. So we have this golden ratio. This is important, like in mathematics, there's few important, very important numbers like E, the base of the logarithms, pi, the ratio between the circumference of a circle and its diameter. Golden ratio, that's another one that's important. There's a bunch of few numbers, not too many, that you should know what they are. So the first thing that we want to show is something about this. First of all, let's see if this formula checks out. Minus 1 over phi, if I want to do that, is minus 2 over 1 plus square root of 5. Is that correct?
Yeah.
Right? And I want to show that is this 1, this is 1. Is this 1 minus square root of 5 divided by 2? Right? That's what I'm proposing here, that if I take this, I inverse it, I put a minus in front of it, would I get that or not? Well, if that would be true, how do we check a fraction to be true? Is this times this has to be this times that, right? In a fraction,
yeah.
A times B equals C by D, we have to do this.
Yeah.
Don't forget there's a minus here. So let's put this minus here. That means minus 4, 2 times 2 with a minus, has to be equal with 1 plus square root of 5 times 1 minus square root of 5. That's the kind of formula we just did, A plus B times A minus B. Remember how much that was? Is 1 square minus square root of 5 square. Is that true? So how much is square root of 5 square?
5.
5. 1 minus 5?
Minus 5.
Minus 4. 1 minus 5 would be minus 4. It checks out? So the first thing we say, okay, if phi is this golden ratio, it's complement. Complement, you need a little bit of topology. the complement of rational, this kind of thing, where this is rational, this is irrational, a plus b, the complement of it is a minus b. Kind of like how complex number works. If you heard of complex numbers, 1 plus 2i, the complement is 1 minus 2i. So in general, for this kind of numbers, complement means if this the integer part stays as it is, but the irrational part, it's with a minus. It's just a name, complement. But we definitely know the complement is minus 1 by phi. What I want to do first, so we're going to prove a bunch of things here. Here's what they are. The first property we're going to prove is phi squared is phi plus 1. That's actually true for the complement. Minus 1 over phi squared is minus 1 over phi plus 1. So the complement satisfies the same quadratic equation. This one is going to imply that phi n plus 1 is phi of n plus phi of n minus 1. That's very easy to see. And this is going to imply the same for the complement. So that's the first part we're going to do. The second part that we're going to do, we put here a 2. We're going to prove that phi of n, phi at n is the Fibonacci number times phi plus phi of n minus 1. The third part that we want to prove put it here. 3 Fibonacci number, that's actually important, is the closed form, is the phi at n minus the complement minus 1 by phi at n divided by square root of I. So that's the formula for the general Fibonacci number. We can compute any Fibonacci number that way. And part number 4 is that we're going to take a matrix, say 1, 1, 1, 0. That's a 2 by 2 matrix. Everybody saw matrices before? 2 by 2 matrix? What we're going to show is that this matrix at the power, so that's n times n times n a few times, is in fact Fibonacci n plus 1 So does everybody know how to multiply 2 by 2 matrices? If I multiply 2 by 2 with itself, what do I get? What size?
2 by 2.
And if I do it again with itself, it's 2 by 2. It's always 2 by 2, right? So I'm going to show that this matrix multiplied with itself actually has Fibonacci numbers in this cells. So that's what we want to do. Those 4 things. Before we do, as part of what we do here, is we're going to talk a little bit about golden ratio. Why is so golden, this ratio? What's so golden about it? Anybody have seen these kind of things about Fibonacci numbers here?
Yes.
Hands up. Out of 1, 2, 3, 4, who have seen 1 golden ratio equation? 2, 1. 3, the closed formula for Fibonacci. 4, the matrix form. So we're talking about new stuff here. That's good. Feels like an honor section. Right. Okay. So here's the story with the golden ratio. Why it's so golden? The golden ratio goes like this. If I want to have a square here, a by a, and I'm adding a part b to it, like I'm making an extension, of course this b is going to be b by a, right? This A by A, that's B by A. There are two rectangles here. Rectangles. A by B, this one, that has B and A. And the other rectangle is the whole thing. Right? That has what sides? A plus B. Right? I have two rectangles. One is this one that I've added here. I'm going to say geometrically look the same. Mathematically means they have the same proportion of sides. So two rectangles look the same if the small side by the big side have the same proportion. So how are we going to write that? A plus B divided by A is the same. So that's for the big one, right? For the big one, the big side is A plus B, the small side is A. How about here? The big side is in this rectangle. A by B. So that's what I want. I want to say I have a rectangle. What kind of square can I add to it to make it look the same proportion rectangle, just bigger, right? This rectangle, it has the same proportion as this rectangle, but I just added a square. That's why it's a golden ratio. This is the phi. So you can instantiate it with, say, of course I can scale this up. So to fix the scale, I can say B equal 1, right? Because I can scale this up and down, I can zoom it in. If B equal 1, how is this picture going to look like? This is 1. If B is 1, A is 1 times phi, that's phi. So A is phi. And then this is phi. The golden ratio is the ratio of the sides of the rectangles, such that if I add a square to the large side, I get another rectangle that have the same proportion. So it's easy to see that that's only one phi. There's only one unique number positive that will have that property. If this will be a little bigger this side, the big rectangle would not have the property. If it be a little smaller, would not have it. So there's only one magic ratio, the golden ratio, for which this happens. So now, how do we prove the first one? That's very easy, right? So I start from here. Who's A plus B by A? A plus B by A, it's actually 1 plus B by A, right? So 1 plus B by A, I would say that's 1 plus B by A is the inverse of phi, right? If phi is A by B, who's B by A? Again, phi is A by B. Who is B by A? 1 over phi. But A plus B here is A by B, which is phi, right? So looking at this stuff here, what did I get? 1 plus 1 over phi equal with phi. Who's following me? Hands up. Okay, any questions? This is just pure arithmetic. There's no magic in here. Just by this equation here, I get it on one side to be 1 plus 1 over phi. The other one is phi. What happens if I multiply the whole thing by phi here? Phi plus 1 is that the part 1? That's proving 1. phi squared is phi plus 1. Right? Again, how did I get from here to here?
Multiply by phi.
I multiply by phi, right? I say multiply by phi. Phi times 1 is phi. Phi times 1 over phi is 1. Phi times phi is phi squared. I can actually verify this. If you don't believe me, I can replace phi. From this equation, I can solve for phi. I can say phi is, so this is a quadratic equation. You remember how to solve those? With a squared x plus b squared x plus c equals 0?
Yeah.
Right. So the equation, the solutions are 1 plus square root of 5 by 2, that's phi, and 1 minus square root of 5 by 2, that is phi complement. Right. So this equation will dictate who phi is. And there are two possible values, but this one's negative, right? Is square root of 5 bigger than 1? So this being negative means the ratio that I need is a positive one. There's only a positive number that allows me to do this, which is 1 plus square root of 5 by 2. The other solution to this equation is the complement, but the complement is negative. Okay? So that's 1, but as part of 1, I have that implication there. That's actually very easy, right? How do I get from phi squared is phi plus 1 to phi at n plus 1 is phi of n plus phi at n minus 1? Right? How do I get from here to here? All I have to do is multiply by phi at n minus 1. Right? So in here, let's multiply this times phi at the power n minus 1. Phi at n minus 1 times phi squared is what? Phi at n plus 1, right? Is phi n minus 1 times phi is phi at n. Phi at n minus 1 times 1 is? Since this happens for the complement too, right? So the complement is going to be 1 minus 1 over phi plus 1 is minus 1 over phi squared. I could get the same happening for the complement, same exact way. If this holds for phi, multiply with phi minus 1, holds for minus 1 over phi, multiply with that one and minus 1, I'm going to get so that's 1, part 1. Let's do part 3 now. By induction. So let's check the base cases first. Let's try phi of 0. How much is phi of 0? Let's just apply this formula. Phi at 0 is 1. Minus this at 0 is 0, right? 1 minus 1, 0. That checks out. How about F1? Phi at 1 is phi equals who? Let's say phi minus, this one is minus 1 over phi, right? Divide by square root of 5. How much is this going to be? Who's phi? 1 plus square root of 5 divided by 2, right? Who is the complement? 1 minus square root of 5 divided by 2. Divide by square root of 5. So what is this? Let's Let's see what this is. So 1/2 minus 1/2.
0.
Square root of 5 by 2 minus square root of 5 by 2.
2 root.
With what sign? Did we all see that? Square root of 5 by 2, that's half an orange, minus half an orange.
Yeah.
It's kind of two halves of an orange. It's an orange, right?
Yeah.
Right. By square root of 5. So how much is this? 1. Checks out. Supposed to be 1. Did we all follow that? Now we need an induction step. What's going to be the induction step, do you think? Like in those recurrences. It's a strong induction. And what did I need in a strong induction to prove my cases? What did I use for the hypothesis? Of course, the result of the induction step is something, something, something implies phi of n is going to be that. Phi of n minus 1 minus phi of n by square root of 5. Of course, that's what I want. But what do I need in the induction hypothesis? I'm looking at here. What did I put here in the induction hypothesis? Where did I get those three things? They were part of the recurrence formula. So what's my part of the recurrence formula? I look at the Fibonacci numbers. What is the recurrence formula on? Maybe I should write this to be clear. Let's write this for n plus 1. n plus 1, n plus 1. What would I need here? N. So f of n is phi n minus 1 over phi n divided by square root of 5. Right? N minus 1. Phi of n minus 1 is phi of n minus 1 minus 1 over phi by n divided by square root of 5. Is n minus 1 here? What?
Yeah.
So this is saying if I know the formula for Fibonacci n and Fibonacci n minus 1, that's my induction step, I'm going to prove it for n plus 1. That's my induction step. That's what I want.
So you just have to add those two and show that it's equal to...
I'm going to use these formulas in here with the phi of n plus 1, which I just proved in there. So that's actually very easy, this proof. Who's fn plus 1? Is fn plus fn minus 1. Now I'm replacing fn, of course, with who I already know fn is phi n minus 1 over phi by n by square root of 5 plus what? The other one for phi at n minus 1, right? Minus 1 over phi at n minus 1 divided by square root of 5. That's phi of phi n. That's f n minus 1. So I'm just doing a basic addition here. I'm going to say phi n with phi n minus 1 go together. Phi n plus phi n minus 1. That's adding this guy with this guy. And the other ones will be a minus 1 phi at n plus minus 1 over phi at n minus 1. Right? I've been adding this one with this one. So I kind of group them differently. I say this plus this. This is a minus here, sorry. Oh, that's a plus. So I've done this plus this minus this plus that. So kind of how much I have in the bank account 1 plus bank account 2 minus debt 1 minus debt 2. That's the sum of the bank accounts minus the sum of the debts. Divide by square root of 5. Now, what did we just prove about phi of n plus phi of n minus 1? There's a formula there. And 1, in part 1. Phi of n, you see? Phi of n plus phi of n minus 1, what is that? That's here, it's phi of n plus 1. Minus, what did we prove about the complement? The complement at n plus the complement at n minus 1, that's exactly the sum I have here, is the complement at power n plus 1. So that's going to be minus 1 over phi at power n plus 1 divided by square root of 5. But that's exactly the formula that I want. That's exactly what I wanted to prove. This thing here is exactly my p of n plus 1, proving the Fibonacci number n plus 1 is exactly this same form. Phi at the power 1 minus phi at the power log by square root of 5. Okay? So we've done 1 and 3 now. How about 2? How about 2? 2 is saying phi of n is phi times fn, the Fibonacci number, plus fn minus 1. Well, let's see some base cases. Also by induction. So what happens if I choose what happens if I choose n equal 2? What do I get? This is who? Phi squared is phi times, who's fn? F2, who's spell table, F2 is what? 1 plus, who's F1? So that is phi plus 1, is that true? Phi squared is phi plus 1? It's something I've already proved, right? How about if I choose, I guess that's enough for base cases, but I could try another one, n equal 3. Phi cube is phi times, who's phi 2 now? 2. Plus 1? You think that's true? We can verify it, right? We know that phi cube is phi squared plus 1. Is that right?
Yeah.
No.
Wait,
It's
phi squared plus phi.
Plus phi.
Yeah.
Right? So that would be equivalent to phi squared plus phi is phi times 2 plus 1. Which will be, I take a phi with a phi, I'll get phi squared equal phi plus 1. So that's true, right? About the induction step. That's a simple induction, I think. What the induction step needs to say. If phi n, so that is p of n implies p of n plus 1. What does this mean is if I know this for n, p f of n plus fn minus 1, how would it read for n plus 1? This equation for n plus 1. Phi at n plus 1 is phi times okay. So how do I prove this? phi of n plus 1 is phi times phi of n. I use the induction hypothesis now on phi of phi n. I know who phi n is. So it's phi times phi fn plus fn minus 1. Right? All I did is to replace phi at n with my induction hypothesis here, the step that I have from the induction. Who's following me, by the way? I know some people gave up. They were in the emails and stuff. But out of the people who's still watching, who's following me, right? This is just arithmetics. Don't get, I mean, some people get thrown off by, oh, there's square roots of 5s. Square root of 5 is just a value. We're not doing anything with it. Phi is a Greek letter. If you don't like phi, replace it with like L, T, whatever letter you like. Same thing, okay? So phi of n, I replace it with this. That's my induction hypothesis. So I'm going to get phi squared fn plus phi times fn minus 1. Now, can anybody give me an idea what to do next? Given what I want to go, I want to get here. What should I do now to kind of get in there?
Can you just shift those Fibonacci numbers? Can you shift that to n plus 1 and then the other one to n?
That's the thing. How do I get from fn and fn minus 1 to here?
Can you do the definitions of those numbers, like fn equals fn minus 1 plus fn?
That's going in the wrong direction.
That's the wrong
I mean, the thinking is correct, but that will not give me fn plus 1. I need to do something about this phi squared, because see, I don't have a phi squared in here.
Can you do common factor?
What?
Common factor?
Common factor is what I started, right? If I take a phi, I go backwards.
Rewrite it into something for.
Turn the phi squared into phi plus 1.
That's what you mean, right?
Yeah.
Turn the phi squared into phi plus 1. So that would be phi plus 1 fn plus phi fn minus 1. I can group the ones with phi now, right? The ones with phi will be phi times fn plus fn minus 1 plus the one without phi is the fn. How much is phi fn plus fn minus 1? Being a Fibonacci number and everything?
fn plus 1.
That's phi fn plus 1 plus fn. I think that's exactly what I want. Right? This is critical for Fibonacci number, that phi squared equals phi plus 1. That's a generative function for the Fibonacci sequence. So that's why everything relies on that equation. Okay, we have one more thing to do, part 4. So let's do part 4, the last induction exercise. What we want to prove is that that matrix at the power n, at any power n, is Fibonacci n plus 1, phi n, and phi n minus 1.
What's the original matrix?
It's right there,
Oh,
1,
so-
1, 1,
oh,
0.
okay.
So let's check base cases. Let's say n equal 1. What would I have? What's m at 1?
1, 1, 0. 1, 1, 0.
1, 1, 1, 0. What will be the Fibonacci matrix? Fn, how much is n plus 1?
2.
2. F2 is 1. F1 is 1. F1 is 1. F0 is? Is good or not? Good. How about n equal 2? What would be this 1, 1, 1, 0? How do I get 1, 1, 1, 0, right, times itself? 1, 1, 1, 0. What is that? Do you guys remember how to do this?
I didn't.
This element here in the position 1, 1 is row 1 times column 1. So I do row 1 from the first matrix times column 1. That's a dot product, so you multiply everybody add them up. So it's 1, again, we see this row times this column. How much is 1, 1 times 1, 1? Plus 1, 1 plus 1, 1. 2. This one here is first row, second column.
Yeah.
So it's still that row, but it's now times this column.
That was 1.
So 1, 1 plus 1, 0.
1.
How about this one? This is second row, first column. Second row, first column. 1, 1, 0, 1. 1. And this one here is second row, second column, which is this row times this column, 1, 1, 0, 0. 1. So n equal to. Well, what is the Fibonacci matrix? How much is F3?
2.
F2, 1, 1, 0. Works. F3 is 2. F2 is 1. F2 is 1. Sorry. You're right. 1. So that's F3, F2, F2, and F1. So what's the induction step? It's simple induction. Is P of n implies P of n plus 1. Which is what? What is P of n? How do I, let's write that again to make sure we follow. So P of n is the fact that m at n is the Fibonacci fn plus 1, fn, fn, fn minus 1. Right? That is Pn. What is P of n plus 1? M at n plus 1 is
M to the fn plus 2.
fn plus 2.
Fn plus 1. Fn.
Where should I start? With the proof. I think I should start here at m at n plus 1.
And take out the m.
Who's m at n plus 1? It's n times m at what power? N. What am I going to do this m at n? Apply the induction hypothesis, right? So who's m, this first m? 1, 1, 1, 0. Right? That's m. And who is, by induction hypothesis, m at n? Fn plus 1, fn, fn, fn minus 1. Right? Now, let's see what this is. Let's do, this is just a 2 multiplication, right? The matrices.
Yeah.
Who's the first thing here? First row times first column.
Fn minus 1.
1, 1 times the first column, this, right? So it's 1 times fn plus 1 plus 1 times fn. How about this one here? Is the first row times the second column. Fn times 1 plus 1 times fn minus 1. How about this one here? Is the second row,
Fn minus 1.
you guys don't see, second row times the first column, right? Second row is 1, 0 times the first column. So who's that going to be? 1 times fn plus 1 plus 0 times, and the last one, 1, 0 times the last column, fn, fn minus 1. It's 1 times fn plus 0 times. So who's this? Fn plus 1 plus fn? Fn plus 2. Fn plus fn minus 1. 1 times an orange plus 0 times something? The orange. And 1 times the same, fn plus 0, that's nothing. Works? Okie dokie. That's induction and recurrences. Happy Turkey Day. I'm going to post more extra credit problems. Extra credits are not required for you to get a maximum grade. They are more challenging problems for people who want to deal with them. Is there online homework? I'm assuming it is. So the extra credit problems are all due in about 2 weeks.
Are you having office hours today?
Yes. Office hours today.
What time? You want to go?